Welcome back to ECE 441, 541. Now that I have your attention, I'm screaming at the people that are online, so I will go ahead and get started. Today's class, to start with the announcements, we have the passport assignment that you can turn in on the assignments page, and that's due Sunday. The pre-quiz is due on the 5th of September. I'm not calling it a prerequisite quiz, I'm just calling it a pre-quiz, just to see where we're at as a class. And homework number 1 has been posted, and I did change the date that it's due. I noticed that they like to work on D2L on Friday evenings from 10 p.m. to 2 a.m., so I said let's avoid that, and now it's pushed off. I think that's a Sunday evening that it's due at 11:59 for homework number 1. What I want to do today is develop a state space representation. We got a good start on that last time, and we'll quickly scroll through what we did last time and jump into trying to define our matrices in the state space representation. Then we will immediately connect that with an all-integrator block diagram, and it should be very easy to make that connection with the state space representation and a block diagram representation. That will be, if it's all-integrator, that's in the time domain, and we can quickly sketch a block diagram that has exactly the same structure in the frequency domain or in the S domain, and we'll do that. Then we'll start talking about a Bode plot for the mass spring damper system, and for that we obviously need a transfer function. But all of these are a part of the modeling process, and I want you to get comfortable with trying to see the system either as a system of differential equations, as a state space representation, as a transfer function, as a block diagram in the time domain or the frequency domain. You need to be comfortable thinking about a system in all of those different ways. We developed these equations or these system dynamics last time. We have the mass spring damper system. It's only one mass. Next time we'll advance and have multiple masses and see how that maybe makes the task a little bit more interesting in terms of finding the equations. And in that case, we would be finding sets of differential equations that would be coupled. Here we simply have one second-order differential equation, and we're labeling the position to be z and the velocity to be z prime. I'm assuming you already have this in your notes, and so for that reason I will quickly scroll through. But some of the key features of this system and its dynamic representation is the fact that it's a second-order differential equation. And that gives us a big key as to what we need to be constructing when we're building a state space representation. In fact, since it's second order, that says we have two state variables. And because we have two state variables, those two state variables, we now need to find an equation for each of those state variables' first derivative. Our state variables are going to be, well, I'm getting ahead of myself. They will be z and z prime, the position and the velocity. In order to start building or constructing this state space representation, it's usually easiest if we start in all of our sets of equations, in all of our sets of differential equations, is to isolate the highest powered derivative in that particular expression. In this equation, in this system, we only had one equation. We can isolate then the acceleration of that mass, z double prime, and put everything else, all our other terms, on the right-hand side of that equality. Now what we want to do is, from this, identify or extract or create two first-order differential equations. This is a second order, so we should be expecting two first-order differential equations to describe that for our state space representation, which means we just keep defining variables, state variables, until we get to the point where if we differentiated our most recently defined state variable, would it give us the highest power derivative in our equation? So we go x1 is z, that's the position, x2 is velocity, and then we start checking. What if I differentiated x2? That would give me the derivative of velocity, which is acceleration, and that's all that I need. I don't need to define an x sub 3 equal to z double prime, because I don't have the third derivative of z anywhere in my equations. So you just start at the bottom and work your way forward until you obtain a state variable with which, when differentiated, gives you the highest power derivative in your equations. That's why I knew that I could stop with 2, and I sort of knew that already when I said, oh, I have a second-order differential equation. That told me I should be looking for two state variables, and now I found those, or defined those, x1 and x sub 2. I think we talked about this last time. So now I need an equation for the first derivative of my state, x sub 1, and I need an equation that is true for x sub 2 prime. And those equations on the right-hand side, so x1 prime will be on the left of my equality sign, and something will be on its right side. X sub 2 prime will be on the left side of an equality, and something will be on the right side. That something can only be a linear combination when we're dealing with linear systems, our state variables x sub 1 and x sub 2, and any of our inputs. And in this case, we only have the one input u. And we start to see if we can identify that. We say, okay, let's differentiate our first state variable, x1 prime. What's the time rate of change of x1 in terms of x1, x2, and u, given the differential equation or systems of differential equations that we have? In this case, the first derivative of x1, since we defined x1 to be z, that's simply the first derivative of z, or z prime. And we want to write that in terms of x1, x2, and u. But that's exactly how we defined x2. We defined x2 to be z prime, so there is our right-hand side, x2. We now have one of our two first-order differential equations. We have x1 prime is equal to x2, and I've underlined that twice. That's what we will use as one of our state equations in our state space representation. The nice thing about state variables is we can extend this easily to nonlinear systems, meaning the right-hand side could have been, if we had a more complicated system, it could be some nonlinear combination of x1, x2, and u. And the state space is clean in terms of we have the same ideas and concepts if we have multiple inputs and multiple outputs. So that's why we want to start learning about the state space, and we typically learn it in the context of single input, single output systems, but we are not restricted to that. We will probably concentrate on single input, single output systems, or a system that just has one transfer function, capital G of S, but we are not limited that with this state space representation. That's why it's important that you start getting comfortable with the state space or a state space representation, or deriving that for any kind of system model that we might have. x2 prime, we do the same thing. We differentiate x2 once, and that now is the first derivative of the velocity in this particular case, which is the acceleration. And we can't leave that acceleration on the right-hand side. We need to rewrite that in terms of x1, x2, and u. Well, z double prime was what we had solved for originally. That was this minus b over mz prime minus k over mz plus gamma over mu. And all of these z's, the z and the z prime, we've already defined as state variables. Z is x1 and z prime is x sub 2. And u is just u. U is u. Right? Y-O-U. No, the letter u. So the input u is u. This is now our second first order differential equation. It's first order because it's one of our state variables differentiated once, and it's on the right-hand side only containing linear combinations of our state variables, x1 and x2. They're just being scaled by coefficients and our input. I sort of like just scrolling, but I'll have to quit that in just a little bit because I'm almost down to the bottom. But this is now, again, you could extend this to some nonlinear system in terms of the concept. For this system, it's a very basic linear time invariant system because our mass is not changing, our dash pot value is not changing, and our spring is not changing with time. What we now want to do is put all of this into some matrices. And I'm guessing you all went home and called your parents and said, we're learning the ABCs in class. I spent an hour. Now you're going to spend another hour with your ABCs. You're going to get that at some point. Your mom goes, we did that before you even got to school. You knew your ABCs. Well, now you're really going to know your ABCs because now we're going to do the A, B, C, and D for a state space representation. And these are matrices, meaning they have particular dimensions associated with them. And in this case, X is actually built up of all of the coordinates that we've defined as state variables. Meaning, if we want the system dynamics, if we're trying to find the first one, which contains the dynamic behavior of our system, the second equation is how you are measuring different state variables or linear combination of state variables, and that's the output equation. But to begin all of this, we need to remind ourselves that our state vector is this long, skinny, or long, tall vector. Actually, it's not that tall for this system. I was just exaggerating. Hopefully you're not taking notes in permanent ink. If you are, well, that's okay if you are. You can just make that point. How many state variables do we have in this system? 2. So our vector x is just going to be 2 coordinates tall, and we'll just stack our state variables in a vector. And the dimensions of this vector, and we'll just keep everything real today. So this is now, these are all taking real values, and our vector is 2 rows by 1 column. X of t is a 2 by 1 vector. And that's now going to help us create this system dynamics equation in our state space representation. What's the vector u of t? Again, it's a tall vector, but in this case, it's a vector that you're going to go, what? It's a scalar. It's a 1 by 1 vector, but it has 1 row and 1 column. We could think of u, and this keeps us then thinking about the generalized structure of this state space representation. You could have multiple inputs. It could have been a force here, a voltage here, another force somewhere else. We might have three separate independently adjustable inputs. Then our input vector would be u sub 1, u sub 2, and u sub 3, and it would be 3 by 1. Now, if we have a state vector that's 2 by 1 and we want to build x prime, we want to take the first derivative of that, that's pretty easy. Now we have x1 prime of t, x2 prime of t, and then we're told that that's some matrix times our state vector plus some other matrix times our input vector. And now we need to determine the dimensions of those matrices. And this is just keeping track of rows and columns. This matrix A that's sitting here, that's our system matrix. That has our dynamic behavior contained within it. How big is it? This equation has to be consistent or compatible, meaning the left-hand side is a vector that's 2 by 1. That means everything on the right better give me a vector that's 2 by 1 when I multiply it and add it together. I now have some matrix which multiplied by 2 by 1 needs to yield a 2 by 1. What's that A matrix supposed to be dimensionally? It's going to be square, isn't it? Your system matrix is always going to be square. Your A matrix is always square, and it's 2 by 2. Now we're dealing with our first equation. And that's our system dynamics. How big is our input matrix, the B matrix? It now needs to take a matrix which, when multiplied by a 1 by 1 matrix, gives us a 2 by 1 vector. So it's going to be a 2 by 1 matrix. It's going to be a column vector. That's our B. And now we need to populate this. In a 2 by 2 matrix, we have 4 elements, and in a 2 by 1 matrix, we have 2. We need to put in the entries in this matrix. So now we go back to our underlined equations, and we say, okay, how do I create x1 prime equal to x2 in that top row of my state space representation? I have x1 prime on the left, and now on the right, I need to only end up with what was on the right, which was x sub 2. How do I build or end up with x sub 2 on the right? What can I put in the top row of that A matrix? So I don't want any x1s in that first equation, and I only want an x sub 2. And by your matrix multiplication, that's rows times columns, this pulls off that x sub 2 from your state vector. You have 0x1 plus 1 times x sub 2. And then how much u do you need in this first equation? You don't want any, so you have 0. That's your top row in this state space representation. And that one's pretty clean. What about the second row? Maybe I should have moved these around because it's nice to go x1, x2, u in terms of the progression. Here's a term that involves x1, and it has a coefficient. Where's that going to be positioned in my A matrix? In the 2-1 entry or the 2-2 entry? 2-1, this is going to be now minus k over m. That's times x1 minus b over m x2 plus the the coefficient that scales U, which is gamma over M, and that will be in the 2-1 entry of the input matrix. That now gives us our system dynamic representation. Here is our A matrix. That's 2 by 2, and that I will typically refer to as the system matrix, and that's distinct from the system dynamics. The system dynamics is that whole piece, that whole equation. The A matrix is our system matrix. That gives us the dynamics. If you looked at the eigenvalues of that matrix, that would be the poles in your system, in your transfer function G of S, and we'll get to that. Here is our input matrix, B, which is 2 by 1, and so we'll refer to that as our input matrix. Everyone's comfortable with where those coefficients or the entries in A and B came from. Let's now look at creating an output matrix. And here I didn't even specify an output yet, so let me just make that call. Let me say that now, let's assume that we want our output Y to be, let's just say that it's the position of that mass. And depending on your particular system that you're playing with, maybe you have a sensor that measures velocity. Maybe that would be your output. Maybe you have a sensor that measures position. Or maybe you have a sensor that you created from the lab and it measures 1 times the position plus pi times the velocity. Josie found that position somewhere in the stockroom and that sensor, and you just used it. That's okay, that's an output. In this case, I'm just picking an output to be Z. Now I need to build up my output equation, Y of t. How big is my Y of t vector? How many outputs did I have in this example? I just have one equation, don't I? I just have a Y sub 1. So I just have one output. My Y vector, my output vector, is 1 by 1. If I had position for Y1 and Y2 was velocity, maybe I had 2 different measurements. Then my output vector Y would be a 2 by 1. It could be position, Y sub 1, and velocity, Y sub 2. But now the output equation needs to be some matrix times the state vector, and you've already defined that. That's just this stacked column of state variables, x1 and x2, plus some matrix times our input vector. And our input vector was a scalar. It's 1 by 1. Now, we need these equations to be compatible, meaning this matrix that pre-multiplies the state vector, what are the dimensions on that matrix? It needs to be such that it gives us 1 row and 1 column. Y is 1 by 1. So how big is C? We call this the C matrix or the output matrix. It's 1 by 2. It has to have 1 row, 2 columns. This is our C matrix. And that one is our output matrix. It now has 2 entries. And we want Y to eventually be Z, but remember what Z was. Z, in terms of our state variables, we defined to be x sub 1. Now, how do I populate my output matrix C? What's in the 1, 1 position of C? 1. What's in the 1, 2 position? 0. And now I have, in the description, I have my D matrix, that I'll call the direct feed-through matrix, that directly feeds the input to our output. What are its dimensions? What's my D matrix? What are the dimensions of that in this example? It's 1 by 1. It needs to give me one row, and it needs to multiply a one row input vector. And this is going to be then my D matrix. And I will call that the direct feed-through matrix. And what is it in this example? I didn't have an input in that particular output. This is now 0, and a lot of times we won't even write that down. We'll just leave it off. It's not there. It's not giving us anything in our output. We fine with this example. Let me give you another problem. Here's the question. Suppose that somebody now says, and maybe your mom or dad did this when you said, oh, I'm learning my ABCs in a controls class. They go, oh, then you can answer the following. Suppose you are given a system that has 20 states. This is getting you ready for exam 1. 3 inputs and 2 outputs. Now, what I want you to do is find the dimensions for your ABCs. Find the dimensions for A, B, C, and D. And if it's not clear today, after this weekend, you should just be able to write this down in an instant, this answer. And then you know what you're trying to create or fill in. How big is your system matrix A? How many rows does it have? Well, that sits just to the right of the equal sign, which has to be compatible with the same number of rows that are in your state vector differentiated once, and that's the same as the number of your rows in your state vector. A has to have how many rows? Needs to be the same number as you had states. And we said, so a check on your work, okay, it now has to have as many columns as your state vector is tall, because it's multiplying. Each row in A is multiplying your state vector. Or you go, oh, A is square. So once you know one of the dimensions, you know the other one. A is 20 by 20. It has perfect vision. What's B? Dimensionally. It now has to have the same number of rows as your state vector, because it has to have consistency with x prime. It has 20 rows. And now how many columns are in this B matrix? It has to be such that it can multiply the 3 inputs in your input vector. It's now 20 by 3. What about your output matrix C? How many rows does it have? How many outputs do you have? You have 2. So how many rows does C have to have? 2, and it has to have as many columns as state vectors or rows in your state vector. C is 2 by 20. What's the direct feed-through matrix? How many rows does it have to have? 2. It has to have exactly the same rows as Y, and we said we had 2 outputs, and how many columns? 3. We're good on dimensions once you know the system, or the number of states, the number of inputs, and the number of outputs. You can create your A, B, C's, and D's dimensionally. Now that we have this state space representation, we can actually build an analog computer. I'm sorry, an all-integrator block diagram. Same thing. Back in the day, we used to play with analog computers, which meant it was just a bunch of integrator blocks, gain blocks, summing junctions, and you could interconnect these wires and solve differential equations on an analog computer. Let's build one on a piece of paper. Okay, so now we want to build an all-integrator block diagram. Which will be for this particular system, which is our MSD, the mass spring damper system that we just worked with. If this is supposed to be solving this coupled system of differential equations, we want coming out somewhere in this all-integrator block diagram, we want to find x1 and x2, and then we can measure those, and we could then have that if somebody injected an input, this all-integrator block diagram would generate the solutions. How do we find x1 if we have its derivative, if we have x1 prime? We need to integrate it. This is an all-integrator block diagram. How many derivatives do we have in this system dynamics equation? We have 2. We have an x1 prime and we have an x2 prime. We need 2 integrators in our all-integrator block diagram. So let's now just put those on our page. We have one integrator and we have another integrator. Now you wished calculus could be this easy, right? There's your integral. Now, going into these, since we want to have this all-integrator block diagram produce x1 and x2, we want this, the output of one of those, to be x1, and the output of the other one to be x sub 2. Now, this is really going to tax you on a Friday morning. If x1 is coming out of an integrator, what must have gone into the integrator? Its derivative. So going in here must have been x1 prime, and going in here must have been x sub 2 prime. And now what we need to do is go back to our system dynamics and create the equation in a block diagram for x1 prime and an equation for x sub 2 prime by combining signals in this block diagram. What was x1 prime? Now you should be able to read it off from this set of equations. X1 prime was? X1 prime is x2, isn't it? We now need to come down here, and in general, we might combine a lot of things. We need the result of a bunch of summations, and they could be weighted summations. We need that to equal x1 prime. But you just told me the only thing that makes up x1 prime is x2, so all I have to do is put that into the summing junction. There's my input to that summing junction. x2 prime, building it, is a little bit more interesting. What makes x2 prime? Let's go at piece by piece. Well, actually, I'm going to kind of pick a piece so that my block diagram doesn't get all messy. x2 prime, let's say it's made up of one piece is minus b over m x2. Right? And I have x2 sitting here in my block diagram. So I can pull that off, scale it by minus b over m, and make that be part of my x2 prime equation. So now everything going into that summing junction has to create x2 prime. x2 prime also has a piece that involves x1, and that's minus k over n. I come down to my block diagram. Oh, here's x1. I scale it. And that's now a part of, or a piece of, x sub 2 prime. Am I finished? Almost, but not quite. x2 prime had an x1, it had an x2 scaled, and it also had a scaled input. And that scaled input was gamma over m. So now I can come back here. I'm running out of room. Must be a Friday. My gammas and m's are getting a little bit messy. Here's my gain, and going in is u of t. Now, if you initialized, let's say that your system had zero, it was at zero position and zero velocity, and now you put in a step. You could apply a constant input for u and flow it through this block diagram, and out would come x1 as a function of time, x2 as a function of time. You've now solved that differential equation via an all-integrator block diagram, or what can be called an analog computer. What we didn't show here was our output. What's our output going to look like? Can we build that by linear combinations of x1, x2, and u? Yes, because we have those sitting there in our block diagram. And in this case, y is pretty easy. It's trivial. It's actually just x sub 1. But it could be some gain and sum that. You can build a summing junction in the lab with some op amps. In this case, it's 1 times x1, and that produces y. But in general, it might be some linear combination of x sub 2, and maybe it even has some input, a direct feed through from the input all the way over. And this block diagram is still valid as long as I put zero gains in there. But now you can see where your different entries are in the block diagram, in the all-integrator block diagram, relative to the state space representation. And in fact, if I gave you this block diagram on an exam and I didn't have anything labeled, I erased the x's, you should be able to use this and produce a state space representation. Try that at home tonight. Have somebody create an all-integrator block diagram. Isn't that what you do on a Friday night? Sketch all-integrator block diagrams? Come on, you're failing me. So pass one to your friend and say, write down the state space representation for this all-integrator block diagram. What would you do? The thing that you really, the only part that you have to remember is I need to label the outputs of my integrators as my state variables. So I label this rightmost integrator's output as x1. I label the leftmost integrator as x sub 2. And then I know what x1 prime is, I know what x2 prime is, and I can just fill in my matrices. And you know with two integrators what's your system or your state vector dimension. You know you have two state variables. This is a time domain block diagram of the mass spring damper system. And from this, you can hopefully see that I could have, if somebody gave me this blind and had all the x's removed, I could have maybe said, oh, I'm going to label this as x2 and this is x1. Dynamically, it's exactly the same. It's just you relabeled things, and now your state space representation is a little different, but it models exactly the same system. That's why state space representations are not unique. That's why I said a state space representation. Let me not leave that on the notes because somebody will get confused. Well, why is x1 x2 and why is x2 x1? Gosh, Tharp, can you be any more difficult? Now we're not. They're not there anymore. But it could have been any way you labeled it. What about if we said that was in the time domain, I want to work with the frequency domain. I want to be in the frequency domain. Now all you have to remember is what does an integrator look like in the frequency domain? 1 over s. The only thing we have to change to put this into the frequency domain is to erase those integral signs and replace them with 1 over s's. Everything else stays the same except the arguments on our variables. Now it would be x2 of s, x1 of s, y of s. Let's do that. This is just fun. I know that you want to go home and do this tonight, so let's just show you how you can do this. So now you could pass somebody an all-integrator block diagram and say, give it to me in the frequency domain. I guess I shouldn't give you so many fun things to do on the weekend, but this will maybe keep you out of trouble. You always have things to keep you out of trouble? Good for you. And I'm not here is the input in the frequency domain, u of s. Here might be capital X sub 2 of s, and maybe this is x sub 1 of s. But this is now an S domain block diagram, or this is now in the frequency domain. Now, somebody says, well, if that's your system, I want to see the frequency response of that system. What are they asking for? They want to excite this system with the sinusoid and see what happens at the output. What's its magnitude and phase at the output relative to the magnitude and phase that I applied at the input. And I want to do that for all frequencies. And then you have your graphic equalizer on your stereo, right? That shows you how you want to adjust your particular stereo to perform in terms of frequency, so that you wanting to pass and maybe those that you're trying to attenuate. But now if you found the frequency response of this system, it tells you how this system behaves for different frequencies. And if we want the frequency response, then we're talking Bode plots. If we didn't have this in the lab to experimentally find the frequency response, you might say, well, I need a G of S. Really? I really want a G of S. It'll cost you. No. How do we find a G of S from this? All we have to do is some block diagram algebra. Did you learn that with your ABCs? No, not quite. What we want, well, we need a G of S. If we don't have that built in the lab to excite it with all of this signaling, we can find G of S many different ways. We've already found it in one of the first lectures from the differential equation, didn't we? Didn't we find a G of S from the differential equation? So we could start with, and since it was just a single differential equation, it wasn't coupled, it was pretty easy to find the differential equation, or to Laplace transform the differential equations and find G of S. That was straightforward in this particular system. We can also find it from this block diagram up above in the frequency domain. We can also find it from the state space representation. We could Laplace transform that state space representation and find G of S in terms of our A, B, C's, and D's. And if you're okay, we'll just continue and do that for a couple more hours. Is that okay? Everybody's free until at least 11. I know that for a fact. I've looked at all of your schedules in U-Access. Pardon? Always a troublemaker. I'm trying to keep you out of trouble, because now you can go 2 hours instead of an hour, right? So how do we find that here? We could, one way to find this is to try to do the block diagram algebra. Suppose that I now labeled this as some new signal W of S. And it's usually when you're doing block diagram algebra, it's nice to write equations for the outputs of your summing junctions. So let me now write an equation for capital W of S. What became of the x1 prime and the x2 prime? I think that was the question. Where did they go? Where did they go? They're hiding in the time domain. This is the frequency domain. So when you're in the time domain, they're there. But if you're in the frequency domain, are they there? No, you don't have primes anymore. We don't have any primes in the frequency domain unless it's meaning something other than derivative. So here are the primes. You can have both block diagrams. Here is the time domain, and you have a prime. So now I have a capital X1 of S. That's the Laplace transform of X1 of t, and that should be in the same location up here where X1 of t was. So if you wanted to prime things, you could say, oh, X2 is equal to S times X sub 1. Meaning, let's look at W of S. Maybe I didn't say that right. W of S is equal to, and now just add up all of the different inputs that generate that output. It's gamma over mu minus b over m x sub 2 minus k over m x sub 1 of s. And now we have so many variables, I'm confused. Gosh, Tharp. But just try to write these in terms of the input and the output. What do you know relates x1 and y? How are they related? They're the same. So we already know that y is x1. How is x1 and x2 related? x1 is 1 over s, so x1 of s is 1 over s x sub 2 of s, which means that y of s is in fact 1 over s x sub 2 of s. Now we can replace all of those x's with y's, and the w, we'll figure that one out next time, and we can write this one equation in terms of u's and y's and find our transfer function from the block diagram. We'll pick up at that point Monday.